Okay, welcome everyone. Welcome to my power system analysis video. Today I have the opportunity to talk about short circuit analysis. Okay, short circuit analysis for any power system engineers is a very important topic. Okay. I would say load flow or power flow is probably the most used power system analysis, but after that, the second most used is the short circuit analysis for many reasons. Okay. Today the topic will be one of the sub areas inside the short circuit analysis. I will spend time today talking about symmetrical faults. Okay. Before I start, please, thank you very much for your comments and your feedback about the videos, and please feel free to go to ResearchGate and download from there my slides. Also, there is a specific GitHub repository that you can find the files, the scripts, the numerical examples using MATLAB. And of course, if you are here, it's because you are in my YouTube channel, okay? Follow me if you wish in Twitter and in LinkedIn, okay? But coming back to the topic today is one of the sub-areas of short circuit analysis, okay? The idea today is that I will introduce the most basic concept related with short circuits. Specifically, this section is dedicated to calculating method for symmetrical short circuits. What I'm trying to say is that today we will be dealing in this session only with three-phase short circuits. Okay, what is the agenda? Well, the plan today is a bit interesting. We will start with the definition of power system states and operation actions. Then I will go around some abnormalities that we can find inside power systems. Then I will go specifically to fault inside power system, classification, then the definition of short circuit, cause and consequence, then stating the short circuit classification, and then I will go for equations, okay? And I will start explaining the dynamic behavior related with the short circuit using a very pedagogical tool, and that is using the circuit analysis of the dynamic behavior of RL, resistor inductor series circuit, okay? Then I will discuss three-phase short circuit calculation methods. Specifically, today we are talking about two specific methods. One related with load conditions, and that is the EMF method. Then we will go for Thevenin method. Finally, some information about short circuit currents and short introduction about circuit breaker specifications, okay? And finally, a summary, and we will finish this session, okay? Okay, let's start with a very interesting and important introduction, okay? Power system, okay? If you're familiar with power system operation, when we are operating the power system, we need to take control actions. I mean, there are some automatic control actions defined by the control system inside the power system, but also there are some actions that the people at the control room and the dispatch center they must cope every single day, every single second by second, okay? What I'm trying to say is that when we concern about power system security, and power system security means keep safe the power system, there are at least four different states, okay? What we call the normal state or secure state, that is the state that all the dispatchers at the control room they like. because we are working with a perfect secure power system. All the variables are inside the limits, because the system is secure, we can perform some economical optimization coming from the economic dispatch, and we keep the lights on, okay? But suddenly something can happen, okay? Something wrong can happen, and from there the electrical variables inside the power system can go outside the limits, and that is when we start to have amber lights, okay? Because there is an alert. We are in an insecure state because there are some situations where the variables are outside the range, okay? Of course, there is a possibility that we take some actions and come back to the normal state. That is possible, especially if we are talking about, for instance, a reduction of the spinning reserve. We can put some generators online, come back to normal state, okay? However, what's happened if this state start to violate or going outside the limits, okay? That we are in an insecure moment. Imagine that we lost a transmission line, or we lost a big generator, and now we are in an emergency, okay? An emergency means that the system is a high risk. We lose all this. We are operating the system in a very important and very dramatic moment, okay? And that is the moment that we need heroic actions, okay? That is the moment that we can try to avoid a cascade failure in your power system. There are protections, there are many mechanisms that they try to avoid the blackout, okay? When we are in extremis, what we are trying to do is escape from destroying the power system, equipment, or the risk to people, okay? And finally, if everything is fine and we took the proper measures, the system will come back in a restorative state, okay? That could be if you went to blackout, you can start to restore your loads and so on, okay? Here I have a very interesting example. In this case, this is a frequency plot, and over there you can see that they are in different colors. Green color for normal state. We have also amber color or yellow color for alert state. And of course, we don't want to go here. That is the emergency state, okay? Those states are defined by frequency limits, okay? If we have a system frequency disturbance, for instance, the largest generator is disconnected from the power system, initially the frequency will go down, okay? We don't want to go so deep, because other case the automatic under frequency load shedding will start to work, okay? We expect that the power system is properly dispatched. We have enough spinning reserve, and the system can oscillate and then start to recover, okay? But in this region, you can see that the frequency is going into an alert state, okay? Because we have here a very fast frequency reduction, but we are expecting that. But here the recovery is a bit slow, and we are going into the yellow area, okay? However, here the frequency recovery is properly done, and as a consequence we reach the normal frequency without any problem, okay? What I'm trying to say is the power system has several states that define the security. We have the normal state, that when we are working inside the limits. If something goes wrong and we start to work outside the limits, we are going to an abnormal state. How bad is the situation will define if we are in alert, emergency, blackout, in extremis, or if we are starting to restore the power system, okay? What I need that you understand is that a normal situation is an insecure state. Insecure states means they are risk that something can go wrong, okay? And I already defined that we are violating the limits or constraints. I mean, voltage too low, frequency too low, or frequency too high. And that is a abnormal or insecure state, okay? The alert state is typically let's say the less dangerous moment, because at that moment we have frequency or voltages outside the scale, and we say, okay, the system is vulnerable. If something more happens, the system can go into a very bad state, and that is the emergency state, okay? The definition is, again, this is an stable state. That means that the system is working, but the variables are extremely outside the limits, but beyond the limits, but the system is still working, okay? Those definitions are taken from the IC 60050, okay? And here you can see the flow chart that you can see, okay, we are in a normal operation, something happened, and then there are some actions that we can take, okay? We can go to the alert state, and from there are possible options that we partially get another state that could be adequate or coming back to the normality, and then we have the emergency states, okay? Depending of them, there is a possibility of having some restoration, coming back to the normal state, or keeping in an emergency situation, okay? Here you can see again, secure state. We are in a normal state, but in this case we have all the variables inside the limits. Then we have the alert state that something potentially wrong can happen, and then we go to unstable, and that is where we don't want to go, okay? Regarding stability, I will provide definitions later in the next class about power system stability. Please keep watching the videos, and you will learn more about power system stability in my next classes, okay? I have a short example here. I will use here the steady state, I mean the power flow, in order to show you what does mean secure and insecure state, okay? If you look here on the left-hand side, you can see there are two generators feeding a load. We are talking about 1,200 megawatts here. And as you can see, there are two transmission lines between one area and the other area, okay? If we have generation unit number 2, 700 megawatts, and this area, of course, they are, assuming they are not losses, the remaining between 1,200 and 700 megawatts, that means 500 megawatts, must come from somewhere else, and that is the other area, okay? As you can see here, 700, the local generation, and we are talking about an importation of 500 megawatts, because there are two transmission lines, we are talking about 250 megawatts in one of those lines, okay? I would like to tell you that in this case, the maximum power that you can transfer, because security constraints and safety, is 400 megawatts in each transmission line, okay? Now, this is the base case. We are working perfectly. Everything is fine, but suddenly one transmission line, the transmission line on the top, the transmission line is tripped, okay? Something happened. Suddenly the circuit breakers open. We lost one transmission line. Now we have a problem, because the demand is still 1,200, the local generation is still 700, and there is a local deficit of 500 that we need to import to the another area, okay? Now we need to import 500, but at that moment, after the contingency was the outage of that transmission line. After the outage, this transmission line will try to go to 500 megawatts, okay? That is an emergency limit. We are above the maximum power of that transmission line. You can see over there that I put fire, okay? That is not realistic, but it's just to tell you that transmission line will be overloaded, because the maximum limit is 400, and we are putting over there right now 500, okay? That means that this is a post-contingency state that is not secure. If this transmission line keep going with 500, we will have a problem. The transmission line will overheat. There are problems with the creep, and probably a second failure, a second fault will happen. Okay, what is the solution? Well, the solution is we need to think about security. Okay. And the dispatch center, sometimes there are some control rooms that they have a security dispatch, and that is considering the N-1 contingency, okay? Again, we have the same demand, 1,200 megawatts, but now what I will do is, well, the local generation will be increased to 800 megawatts, okay? What does it mean? That the total importation of power coming from the other area should be 400 megawatts, okay? In this case, we have two transmission lines. We are assuming that both of them have the same impedance, and a consequence, 200 megawatts on the transmission line on the top and 200 megawatts on the transmission line on the bottom, okay? And of course, those 400 megawatts are coming from the other area, okay? Generator is producing 400 megawatts. Again, we are in a lossless power system, okay? Okay, and now if we have a contingency, in this case, the transmission line on the top is tripped. Now we have no power going through that transmission line, but the second transmission line must take the whole load, and in this case we are talking about 400 megawatts going across the line, the transmission line. However, that is the limit, the secure limit, the normal limit for that transmission line, and as a consequence they are not overloading elements, and we can say this is a secure state, okay? Now, what is the question? The question here is, okay, we are talking about security. Right now, we have a system that is able to survive, and there is not element overloaded as a consequence of the contingency. Okay, that is what some people from the control room call this at optimal dispatch secure constraint. Okay, it's a very hot topic in recent time. Especially including variability coming from renewable resources, okay? If you want to learn more about optimal dispatch, and you can read more in my favorite book, Wood and Wallenberg, okay? But coming back to this problem, the original situation was this generator on the right-hand side, 700 megawatts, and the other one was 500, okay? That can be done, or that can be the solution coming from optimal power flow. That means that is the most cost-effective solution. But taking measurements to include security, in this case means increasing the power on the generation unit 2 and the generation 1 decrease. Now I want that my student reflect what is the cost of making that change. Okay, what I'm trying to say is, time to time, people from the cost and the financial area, economic area of power system, they would like to optimize the power system in order to run a minimum cost. Yes, I love that. But if you consider only the operation cost and you don't consider security, then you can have problems, okay? This is just a reflection that I want my student come back again and think about the cost of optimal dispatch, including security, okay? Okay, now we are clear that we have the normal operation of the power system, and then we have some states, that they represent abnormalities inside the power system, okay? What are the typical abnormalities inside the power system? Okay, the first thing that you must understand is those abnormalities are coming from many different causes, okay? There is a possibility that the abnormality inside the power system can come from a fault or a failure of one of the components inside the power system. Minutes ago, I was talking about a transmission line that was outside the service, okay? Out the service, okay? But however, there are many possible options. In recent times, the phrase or the word resilience has become quite popular inside power system society, and that is coming with that is coming from the reality that there are very low probability events that can happen, but with a massive impact inside the power system. For instance, Katrina. Some storms, they have the possibility to shut down the full power system, okay? What I'm trying to say is they are very strange situations in nature and also in human behavior that they can create problems inside the power system. Storms, snow, floodings. There are many situations that they can cause that the power system work in an abnormal condition, okay? What is the consequence of this abnormality? Oh, I forgot. another reason that the power systems can work in an abnormal situation is also the human beings that they are working inside the power system. I know that my colleagues and friends from the dispatch center, they will be mad, but sometimes human beings, they make mistakes, okay? That is a possibility. Human beings making mistakes at substation level, trying to open a switch under load, that can create problem. Or also a mistake coming from one of my colleagues from the dispatch center, that can create abnormal situations, okay? But what is the consequence of that? The consequence of that is that we have bad service. That is the best case scenario, okay? The customers, they have voltage outside the limit, frequencies start to going down. That is the best case scenario, okay? But there are very bad situations that we can have, for instance, a loss of stability of the power system and as a consequence, a massive blackout. That is the worst case scenario. We don't want a blackout. That is the nightmare of somebody working in the dispatch center, okay? And of course, beyond the blackout, there are another possibilities. I don't want to go there, but there is a possibility that we have equipments that they are damaged because the abnormality, and also there is a possibility that people die from this, okay? I will not go there. What I want to say is that the power system abnormalities can be classified in two very broad areas, okay? One of them is faults. That is the topic that we are covering today, later today. Faults are probably the most severe phenomenon, abnormalities inside the power system. And there are some others that they are called disturbance, okay? Let me start with the disturbance. The disturbance, they are typically not so dangerous at the first glance, okay? It's a condition that allows the operation of the power system, okay? However, one of the problems of the disturbances is that it's the sighting point of something inside the power system, okay? A disturbance, you can have some limits that they are, some variables that they are going outside limits, but then if the situation keep going for a very long time, you can have problems, okay? What are the typical disturbances? Typical disturbances, we can have three sets of them. Overvoltages, that is an abnormal voltage rise. Overload, that is a very, that is when the current go above the maximum current. In this case, the overload could be permanent or could be a short duration, okay? Short duration, for instance, an induction motor that is starting up, okay? And finally, we have something that we will cover later in power system analysis and power stability, and that is power oscillation, okay? I forgot to say overvoltages is quite interesting topic. Overvoltages are mainly related with the energy transfer inside the electric field, but from the power system point of view, we can classify the overvoltages in mainly three difference, okay? Some external overvoltages coming from the atmospheric phenomenon, the lightning strike, and some internal overvoltages coming from switching switching inside the power system or related with some temporal situations, okay? However, again, disturbances is not the main subject today. The main subject today is related with faults, okay? Faults are conditions that prevent the operation of one or more devices inside the power system and require the rapid intervention, the quick intervention of the protection system, okay? In order to avoid equipment damage, and I didn't include over there, and also hazard for people, okay? The electrical faults is typically caused by two different things. One of them is related with the lack of insulation. That is what is happening in short circuits, and that is typically related with lack of insulation, or the insulation is broken. Okay. The other step is that we have discontinuity on the supply, and that is a serious fault. Okay. What I was trying to explain in short words is that the faults could be several types. Okay. They are what we call the shunt faults, and that is the topic today, short circuits. They are serious faults. A lot of people they disregard, or they don't give enough credit to the open circuit faults. Okay, open circuit faults, they are very important, especially at ultra high voltage. Okay. And there are some other kind of faults, something that we call winding faults, and that is typically related with machines, rotating machines and transformer. Something that is not covered here, simultaneous faults, because the probability is extremely small. What's happening if we have two short circuits at the same time at different geographical locations, okay? And finally, there is something called evolutionary faults, and that is a fault that starts with one condition and then is changing over the time. Okay? Okay, we are clear now that we are working with faults, and to be honest, this class today is related with one of those faults. Okay? The remaining of my session, when I say faults, I will be talking about shunt faults. I mean, shunt faults are terminal conditions related between the line and another line, or going back to ground, etc. Okay? Shunt faults, they receive the name shunt because they represent a shunt connection, shunt terminal connection. Okay? The typical shunt fault is the short circuit, the short circuits. And when we are talking about short circuits, we can talk about symmetrical faults, that is the topic today, and asymmetrical faults, that is the topic for the next videos, okay? On the other hand, I will not cover here the series faults. Series fault, they receive the name open circuits. If we have a three-phase circuit, we have two options of open circuits. A single line open, or one open conductor, and there is the second option that is two open conductors. Okay? Okay, let me keep going here. And what is the definition of a short circuit? As future professional engineers working at utility, I highly suggest that follow standards and be very serious with your concepts. For that reason, I am using IEEE standards 100 that define a short circuit as an abnormal connection, including an arc of relative low impedance, whether made accidentally or intentionally, between 2 points of different potential. Okay? I don't know if you realize, but here we cover all the flags. First, we are talking about a low conductivity path. Low conductivity path. Okay? Then that path is between 2 points or even more, but those points, they must have different potential. And third, this short circuit could be accidentally or could be intentional, okay? On the other hand, here in Europe, we have the European standard IEC 60909. That is the typical standard for short circuit calculations here in Europe. And this standard say that the short circuit is accidental or intentional conductive connection through relative low resistance or impedance between two or more points of a circuit which are normally at different potential. Again, you can realize that both concepts have common grounds, intentional or accidental. Second, a very low conductive path. We are talking about low resistance or low impedance. And then again, we need different potential between the parts, okay? Okay. Now, from my point of view, I want that you understand that first, the short circuit is a transient phenomenon, okay? A short circuit is transient phenomenon. Both definitions from IC or from IEEE, they don't include this, but it's extremely important that you understand that it's a transient phenomenon, and later you will realize that over the time, the short circuit current is changing, okay? What we need is a very low path, impedance path. We need differential potential between the components, okay? Something that is really important is short circuit condition is something that is a fault. And the impedance that is related in this condition is extremely low, okay? Because the power system is designed to minimize the losses, and a consequence resistance, reactance, they are extremely low, okay? And when you have a fault, when you have a short circuit, you are creating a shunt path for currents. And in this case, the short circuit currents could be very, very large, okay? We are talking about, I know that people from industry and from the utilities, they will say, okay, you are saying numbers that probably can be just generic, but no, there are many specific cases that they don't follow that, okay? However, my young students, they must realize that the short circuit current is extremely high, okay? It could be several times in the majority of the cases, it could be several times the rate current or the nominal current, okay? That is the reason that is extremely important that you must take in account short circuit analysis, okay? And because the short circuit depends on the total impedance in your power system, you must take in account that the short circuit levels can change depending on many factors, but there are few of them that they are quite typical. One of them is the number of generators connected into the grid, and especially the configuration, okay? Okay, now let's briefly talk about what are the causes of the short circuit. There are many causes for short circuit, however, we can classify them in three specific areas. Electrical causes, that they are coming internal or externally, but they are mainly related with broken isolation, okay? The isolation can be affected by many reasons, especially over voltages coming from atmospheric over voltages, lightning strikes, or coming from internal over voltages from switching or circuit open circuits operations, okay? Anyone taking a course on high voltage techniques must realize that switching voltages, especially for ultra high voltage, they are quite important, okay? From the mechanical point of view, wow, there are many reasons that can create a short circuit. Coming from the very basic, like the insulator link or insulator string is broken, or one excavator destroy an underground cable, or even an airplane or helicopter going across the line, okay? On the other hand, finally, we have electrical and mechanical classes, but The third class is covering anything else that cannot be included on the other causes, okay? That includes, for instance, human errors. Human errors, sometimes they can create short circuit. For instance, at substation level, imagine that you have a circuit breaker and the dispatcher didn't realize that the circuit breaker was closed, and he tried to open the switch connected to that. Switches, they are not designed to interrupt currents, and as a consequence, you will create a problem with isolation, and then there is a single line connect to ground by a big arc, okay? Very dangerous situation, okay? Another way to classify the short circuits, there are many ways to classify the short circuits, but another way is depending on how the contacts between different potential places inside the power system are taking in action, okay? What I want to say is that there are some short circuits that we say that they are coming from direct contacts. I mean, there is almost zero impedance, and that is, for instance, when two lines in a transmission line, they have contact between them, okay? That is not a typical situation, but that can happen, okay? Insulation breakage, that is another reason. Typically, when we have air and we have over voltages, there is an electric arc, and that electric arc, as a consequence, can go across the air, and there is a dielectric breakdown, and we have a short circuit, okay? That situation is quite typical. It can happen for many reasons. It can be external, it can be internal, okay? Okay, what are the consequences? Okay, short circuits. We don't want short circuits inside the power system for many reasons. One of them, starting from probably the basic one, we will have massive currents moving. Okay, again, my people from the TSO, they will say that depends on the situation, but in general terms, we have very high current moving inside the power system. And very high currents means that you will have currents that could be several times the nominal current. You are overloading your devices, and as a consequence, you can have very bad situations, overheating your cables and many other things, okay? And because we have those very big currents, there is a problem for loading some equipment, especially the expensive one, generators and transformers, okay? We don't want short circuit currents moving inside the transformer for very long, because you are frying, you are making a barbecue with the transformer. You don't want that, okay? It's difficult to explain right now because that is mainly a consequence for asymmetrical faults, and that is the topic on the next class. But there is a possibility that during asymmetrical faults you have some healthy phases or healthy lines, that there is a big problem of over voltages, okay? And on the other hand, if we have a faulted line, especially in three-phase short circuits, you will have the pressures, the voltage going extremely down in a very specific places nearby to the short circuit, okay? Wherever the situation is, the consequences are not so good. We don't want short circuits inside the power system. We need to take care about power systems, faults inside the power system. And that is the reason that we have a very specific and important module talking about power system protection, okay? Okay, but now let me go for the short circuit classification, okay? This slide is a zoom in of what I was explaining previously. The faults inside power systems, they are shunt faults, they are short circuits, and we classify the short circuits in asymmetrical faults and symmetrical faults. Main difference, wow, there are many, but what I want that you understand is three-phase faults, they are symmetrical faults, okay? And the mathematic tools to solve symmetrical faults and asymmetrical faults, they can be very different, okay? What are the basic and most known symmetrical faults? The short circuits. However, you can see here the short circuit can happen between the three lines here, or it can be between the 3 lines and ground together, okay? On the other side, and that is the topic for the next class, we have the asymmetrical faults, and we have line to ground, line faults, and line to ground faults, okay? However, the class today is only dedicated to the shunt terminal condition that is related with 3-phase faults. 3-phase faults, they can be created by connecting 3 phases together, and that is the case of the 3-line short-circuited. Or on the left-hand side, we can have 3-phase fault to ground, and there is connection with the ground or earth, depending if you're in America or in Europe, you will use different names. However, what I need that you understand is those are the terminal conditions for 3-phase short circuit, involving earth or ground and not involving ground. Asymmetrical faults is the topic for the next class. However, asymmetrical faults that represent the connection of one line to earth or ground, 2 lines. There is something that in some countries they call 2-phase or B-phase, I don't know, whatever, biphase, whatever you want to use the name, but it's the contact between line to line. And there is 2 lines to ground, okay? Again, asymmetrical faults. Asymmetrical faults is the topic for the next class.